Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Laplace's Equation, Fourier Series, Synthesis, and such. And I did recommend that you watch this because this is a nice development of the physics behind Laplace's equation. But we're not going to present that derivation in this video. So Laplace's equation in 2 and 3 dimensions occurs in time-independent problems. That means it's steady state. There is no change with respect to time. And this is involving potentials. And that's a loaded word because potential functions were something that you studied in your Calculus 3 at the College of DuPage, was finding potential functions. And it involves applications including electrostatic, gravitational, and velocity and fluid mechanics. Moreover, a solution of Laplace's equation can be interpreted as a steady state temperature distribution. And that means if you had a hot plate and you had a constant source of temperature, the temperature would vary depending on where you put the probe to measure the temperature, but it would be a constant with respect to time because you've got a constant input there. So that's like one manifestation of this. Laplace's equation in 2 dimensions and in 3 dimensions is abbreviated as, and this is the gradient times the gradient, that's also called the Laplacian. And those of you in your Calc 3, remember that's the dot product of del with del. But what it means in 2 dimensions is the second partial with respect to x plus the second partial with respect to y. And in 3 dimensions, it's the second partial with respect to each one of those variables added together. So those are called, and that operator is called the Laplacian, and these are the Laplace equations. And this is, again, in general, what the Laplace equation is going to say. So it's equal to 0, and these are your spatial variables, spatial, S-P-A-T-I-A-L. Okay, so suppose we want to find a steady state temperature. We're using that as our example here, but it applies to any of those. U of x, y, so there's no t. In a rectangular plate with vertical edges, x equals 0 and x equals y are insulated. So if you look down here, you've got the insulated there. And so no heat escapes from the lateral edges. And that means that at 0, the heat crossing there is 0. And at A, the heat crossing that is 0 because those are insulated, and that's all the way across there for any values of y, so from the bottom to the top. Also, what we have is that we have U being 0, the temperature is 0 down here, and it's equal to f of x on the top. So that's what we have as our initial conditions and as our boundary conditions. So you see, this problem has initial conditions and boundary conditions. Okay, so let's wade in and solve this then. So we'll start, as we have many times, by saying that, well, U of x, y is capital F of x and capital F of y, and we're going to try the separation of variables. And again, you've seen this many times. But this time you get, this is my equation for x, and this is my equation for y. So we start looking at the x equation, and we get this as for our initial conditions, and we start examining the cases. Lambda equals 0, lambda being negative, and lambda being positive, which we've done several times already. So when lambda equals 0, you get this as a solution, but the boundary condition implies that x1 is equal to C1, but if C1 is not equal to 0, then you have a non-trivial solution. It is a constant, but it's not 0. For negative, you only get the trivial solution. You should be able to work through this, but we've done this several times. And for positive, what you get is this differential equation, and we've done this a couple times before as well. You know it's a linear combination of cosine alpha x and sine alpha x, and you work through it, and you find out that what happens is, now this time though, what happens is you get the same eigen values that we've gotten many times, but this time your eigenfunction, because of the conditions that we have, is going to be a cosine rather than a sign. And over here for n equals 0, it's going to just be a constant. Now we're going, so we've dealt with the x, and we know that that's what we have for each value of n. Now we go to equation 5, which is the other one. Now notice that the SIGN of lambda is different. So that means that we're going to solve this, but y of 0 implies that C1 is equal to 0. So the solution here is that y is equal to C4 of times y. And we get the same eigenvalues, but our eigenfunctions then have a different SIGN because of this sign being different. So instead of being the cosine and the sine, these are the hyperbolic cosine and the hyperbolic sine. And so, and we end up with this being the solution associated with that eigen vector. So now the product then of those, it does depend on n, is going to be this and this. And we did a little bit of rewriting of the constants. Okay, now so we have to figure out what are these a's. Well, and we also say, oh, and you could add all of these together for u of xy. This is the superposition principle again. So here's the general solution. And so now we're going to use the last boundary condition, which was x is equal to b. So if we substitute x, not x rather, it is, wow, I think that is, we're substituting b in for y. That's a typo, I'm sorry. You're substituting b in for y, and this is what we will get when we substitute b in for y. I'm glad I caught that as I was reading through. I should have caught it before. And so, and this is starting to look kind of familiar because that is very close to being a Fourier series, but it's a cosine Fourier series. So we, again, mess around with the constants. We're going to call this a0b a0 over 2, and this we're going to call a n, because that is, after all, just a number. It does depend on n, but that's just a number. N's a number, a is a number, and b is a number. So the hyperbolic sign of that is a number. So we have that. So this is what we get for a0. Well, so a0b is equal to this this integral, because what we're doing is we're really just multiplying all the way through by the constant's going to be that, because this is n equals 0. So the cosine of 0 is going to be 1. So that gives us 1 there. So that is what the constant is. That tells us that a0 is this. And we do, again, now this time we multiplied all the way through by m, but the only time we're going to get something is when the n's match. So we're going to get, this is the coefficient for a sub n. Now notice I still have this factor, so I do have to divide both sides by that number, but that is what the coefficients are for that. So you see, we did use Fourier series again, and using those coefficients, that's the solution to the one Laplace problem that we're going to do. Now I'm going to do a little bit of a synthesis of some things we've talked about. PDEs, like ordinary differential equations, are classified as either linear or non-linear. And analogous to a linear ordinary differential equation, the dependent variable and its partial derivatives in a linear PDE are only to the first power. For the remaining chapters of this text, and we're not really doing a whole lot of that, but for what we're doing, we're still focusing on linear second order PDEs. Now, in addition to that, a linear second order partial differential equation in two independent variables, and so you have a x and a y, for example here, with constant coefficients, can be classified as one of three types beyond linear and non-linear. These are linear already, but this classification depends only on the coefficients. And so we have, this is the general linear second order partial differential equation that we have, and all those capital letters are constants. So it is hyperbolic if b squared minus 4ac, that should look familiar to you, is bigger than 0. Is called, and by the way, if you think about what we've studied, the wave equation is an example of a hyperbolic PDE. A parabolic PDE is if b squared minus 4ac is equal to 0, and the heat equation is an example of that. And it is called elliptical if b squared minus 4ac is less than 0, and that is Laplace's equation. So you see, studying these gives you insight into these broader categories of partial differential equations, and some people become experts in one of these and not the others. This is a very rich field. Okay, so now some remarks. Separation of variables is not a general method for finding solutions. Some PDEs it works and some it doesn't work. And here's an example, and a serious student may want to try this to prove, but separation of variables will not work with this, because what you got is you have an x over here that will cause you problems. Number 2, a detailed explanation of why we classify these things is beyond the scope of what we're talking about, but the classification is of practical importance. Some PDEs you sell only according to boundary conditions. We saw some of those, and others we use both boundary and initial conditions, and Laplace's equation was one of those. And the kinds of side conditions that are appropriate depends on whether it is hyperbolic, parabolic, or elliptical, and approaches to doing numerical solutions for linear second order PDEs is different depending on the classification. So it is of practical importance. Okay, now the analysis of a wide variety of diverse phenomena yields these models: the wave equation, the heat equation, and Laplace's equation. And it is sort of like when we studied the vibrations, there were many problems that we could solve based on that. The same thing is true here. And so, and some of these generalizations we talked about in one dimension, there can be many special dimensions. Special, S-P-A-T-I-A-L, again. The heat equation is sometimes called the diffusion equation because the diffusion of dissolved substances like chemicals in a solution is analogous to the flow of heat in a solid. I also will tell you that diseases work in a similar way, the spread of rumors and things like that. So it's a very significant kind of thing. Similarly, equation 2, which was the wave equation, arises in the flow of electricity in a cable or a transmission line, and they say that's called a telegraph equation. And the current and the voltage are functions satisfying two equations that are identical with the wave equation. Also, in quantum mechanics, the wave equation is a Schrodinger's wave equation. Let's see, the wave equation also appears in the theory of high-frequency transmission lines, fluid mechanics, acoustics, sound, and elasticity. It's interesting that you get the same formula for sound waves, even though sounds are not transverse waves. They are what is called longitudinal waves, and elasticity. And last but not least, Laplace's equation is countered in membrane displacement and many other kinds of things as well. And in fact, study of Laplace's equation leads to a whole general thing called harmonic analysis. It's a huge field. Okay, so looking back, Fourier series arose repeatedly when we were solving those equations of mathematical physics, and so it's important. And we're going to conclude our course with a mathematical treatment of just Fourier series by itself. That's tomorrow's work. As you will see, it is a rich field with powerful applications well beyond those discussed so far: digital signal processing, voice compression, so on and so forth. And damn, there is so much to learn and so little time, but we'll do our best. In closing now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.